Welcome to the second edition of our Earth Leakage and Earth Fault series. Thank you to all who have tuned into the first edition, and we trust that the content was helpful in clarifying some of the issues associated with this subject. Firstly, let's recap on edition number 1. In that presentation, we covered the difference between earth leakage and earth fault and discovered that it was really the same thing, only different in application outcomes and in magnitude. We looked at the standards involving the testing, performance and classification of detection devices, namely RCDs and earth leakage relays. We covered the need for detection of different waveforms and types of RCD used to detect and interrupt them, and we also took a brief look at different types of RCD and earth leakage relay. The final section, we touched on earth fault and how we commonly detect, measure and interrupt the event and why. In this presentation, we'll be referring to a number of standards associated with the subject matter, specifically AS/NZS 3190/2016, current operated earth leakage devices, AS/NZS 3000/2018 wiring rules, AS/NZS 2081 2011 electrical protection for mines and quarries, and AS/NZS 4871 2012 electrical equipment for mines and quarries. Now we'll move into more specifics and applications regarding earth leakage and earth fault. Earth leakage relays and applications, AS/NZS 2081/2011, and specific requirements for earth leakage and earth fault. The RCD applications in detail, and requirements of the Workplace Health and Safety Act. So let's dive straight into the requirements of AS/NZS 2081 standard with regards to earth leakage protection in mines and quarries. My colleague and good friend Victor Kudwa, application engineer from Western Australia, has studied and prepared much of this content in an effort to clarify some of the specifics that are unique to these applications. Much of the confusion in our industry is around what earth leakage devices actually meet the brief as suitable for use in these applications and why. The 2081 standard covers earth fault current limitation, earth continuity protection, earth fault protection, earth fault lockout protection, NER or neutral earth resistance integrity, and frozen contact protection. It does not allow standard types of RCD protection to comply to the AS/NZS 3190 standard or the 61008 and 61009 standards because of these requirements. The standard AS/NZS 2081 nominates the performance and design for electrical protection devices used in mines and quarries. In association with AS/NZS 4871, it provides guidance on techniques for earth leakage and earth fault and mitigation, as well as prevention in danger caused by rise in touch voltage potentials on machinery used within the system. The major difference with the mining and quarrying reticulation system is the use of the IT network and earthing systems. In many mining applications, standalone generator systems are used for power supply to the site. The IT system is best for maintaining safety in areas where there is abundant rock and broken ground. The rock and broken ground causes poor earth continuity and conductivity in the grounding system if the normal MEN system of reticulation was used. The IT system does not use a low impedance interconnected earthing system, as does the MEN system. It uses an earth star point at the step-down transformer with a high impedance resistor or reactor to limit the earth fault currents. The result as far as earth leakage goes is an aim to limit the possibility of a dangerous voltage being present on the frames of plant and machinery used in the operation. The earth leakage relays placed in the reticulation system have specific requirements and must constantly check and recheck the occurrence of earth leakage current, as well as their own connections, their own performance and their accuracy, and also check for the system warning and lockout integrity. So what devices do comply to this standard and why? This is a typical system wiring diagram from an earth leakage relay with all components and functions shown. Firstly, they need to provide earth fault protection, and in the IT environment, earth fault currents are greatly suppressed by way of the high impedance resistor or reactor located at the transformer star point. Therefore, detection and interruption of earth faults must be performed by the earth leakage relays in that system. The standard calls for settings of between 0.1 amp or 100 milliamps and 5 amps. The relay needs to have earth fault lockout protection, frozen contact protection, as well as self-checking functionality. The core balance toroid needs to have a primary measurement circuit as well as a test circuit. These perform a number of functions. The test winding circuit is connected to, in this case, the DSR TD48, and this unit sends an impulse through the winding, which is picked up by the primary winding, confirming that all connections are intact and the system is functional. Here is a typical 2081 approved earth leakage relay and test module. The front face panel should have a number of adjustments and controls to enhance functionality in the system. An adjustable trip current dial. Now clause 6.2 calls for sensing current less than 0.1 amps and up to 5 amps. In this case, adjustments from 0.01 milliamps to 0.5 milliamps. The dip switches in this case serves a number of purposes. Firstly, as an I delta N multiplier, times 1 or times 10 of that setting on the front face panel, and this takes the setting possibilities standards up to 5 amps, as the standard specifies. Clause 6.3 calls for maximum operating time, and it shall not exceed of 550 milliseconds. This should equal around 500 milliseconds maximum setting and 50 milliseconds clearing time of the controlling switch device. There is a time delay in this case between 0.05 seconds or 50 milliseconds and 0.5 or 500 milliseconds. This dial has no multiplier for obvious reasons. The levels are set according to calculations based on plant and equipment startup needs, as well as the acceptable time for the existence of earth-initiated touch voltage rise within the installation. It's also to allow selectivity with devices downstream to trip instead of compromising the entire supply system when there is a localized fault. Clause 6.4 states that incorrect wiring or malfunction of any one system component will trip the relay. The second dip switch sets the status of the output relay. It can be ND, or normally de-energized, or NE, normally energized. If the relay is set to NE, it means that the relay is held in the armed position while power is connected to the system. If power is lost, the relay fails to safe, tripping the controlling circuit breaker or control device. This is also the case in the event of fault detection, either a system fault or an earth fault. The AI dip switch setting gives a choice of either 2 auxiliary relay outputs or 1 trip relay and 1 power fail flag relay with negative security functionality, or ND. ND is normally de-energized and NE is normally energized, as stated earlier. Clause 6.5 states that automatic reset functionality is not allowed. Local and remote reset is allowed only. This is a local manual reset button and relay test button. The relay also features LED proportional leakage indication from 20% to 50% of the set trip level. Here are a few handy installation recommendations to avoid issues in operation and system integrity. Preferably the connections to the toroid should be made with shielded cable and no more than 5 meters in length. If it is not possible to use shielded cable, twisted pair conductors are recommended. The cable should be segregated from all other forms of induced magnetic fields, including current carrying cables and electromagnetic devices such as contactors, etc. The toroid likewise should be separated by at least the extent of its own width to avoid induced signals. The toroid chosen should be the smallest unit that allows the tightest fit of cables through its core. And you should only use the toroid which is recommended by the manufacturer of the relay for the application. Otherwise, nuisance tripping may occur and there may be a possibility of relay failure. Finally, single conductors for each phase ensures a more accurate reading. Multiple phase conductors may alter the result. In any case, run the conductors as closely to the center of the toroid as is possible. Let's now look at some other unusual situations and applications and work with some issues we've discovered along our journey in the application engineering field over time. There may be some situations where cables are too large to fit through the toroid or where the use of bus bars in the switchboard make it impossible to successfully mount the appropriate toroid. In the case shown here, tripping was caused by the failure of the middle bar to induce a balanced amount of current into the toroid. In these cases, the most successful remedy is to install the Holmgreen method of detection. Now beware, the Holmgreen method of detection is not an approved method for mining applications and does not conform to the 2081 standard necessarily, depending upon the type of relay which is used to do the detection. In this case, specially tested and selected current transformers that have closely matched characteristics are chosen, and these are installed on individual phase conductors and connected to a special summation current transducer. The transducer ratio is matched to the current transformers and input to our RD type relay in this case. Now for applications where primary current is above 400 amps, a specially calibrated relay with 10 times I delta N adjustment range must be requested and used. As with other current transformers and toroid applications, care needs to be taken that the measurement winding is routed away from the induced current influences. Now here's a quick tip regarding repurposing of 4-wire toroids and connecting to a 2-wire earth leakage relay. If there's no requirement for a 4-wire toroid to comply with AS NZS 2081 ELR and is being replaced, the test winding of the toroid can be rendered ineffective by connecting a 1 k-ohm resistor across the test winding leads when they are disconnected. This prevents stray signals being produced and causing nuisance tripping of the new 2-wire earth leakage relay. On another matter, an interesting problem with earth leakage tripping was remedied in a tower lighting application on a roadway lighting project in Perth, Western Australia. And it's appropriate that we share this because it's a conundrum that our industry faces in many of these applications. So with approximately 200 metres between the lighting towers, underground cables supplying the lighting towers were installed in conduits along the length of the roadway. When the installing contractor came to energise the towers, so there were 4 towers supplied from 1 breaker in a distribution board, the RCD controlling the supply tripped. The contractor switched off the 4th light tower and tried to energise again. Immediately the RCD tripped again. The contractor isolated the tower 3, and the isolators for all of these cases were located in each tower base to allow them to isolate each of the lights on top of the towers. But in this case again the RCD tripped. The contractor isolated the lights in tower number 2, but again the RCD tripped. He then isolated the lights on tower 1, but the RCD still tripped with no current flowing in the circuit. So what could be the issue? Leakage in the cables and in the conduits. Could that be the case? So, to help explain this, in this slide, I'm going to introduce a capacitor symbol to the conundrum. In reality, any conductors of different potential running parallel to each other has some sort of capacitive potential, just like the plates of a capacitor. The greater the surface areas exposed to one another, the greater the capacitance and lower the capacitive reactance. Now, capacitive reactance is the resistance of AC current to exchange across capacitor plates, just like resistance, but we call it capacitive reactance. And that stops the electrons from moving from one plate to another. The type and thickness of the dielectric also has limiting factors and alters the capacitive reactance between the conductors. So understanding now that this is a possible issue, let's see how we resolve this issue in this case. Now the contractor removed the conductors from supplying tower number 4 from the connection in tower number 3. The RCD still tripped. Observe how the length of the capacitor plates that I've illustrated in the bottom have also changed along with the length of the cable that's connected. He removed the conductors from supplying tower 3 from the connection in tower 2. In this case, the RCD remained closed. So what could be the problem? The contractor then mega tested the cables running from tower 2 to tower 3 and he found no issue. He was testing from tower 3 to tower 4 and still no issue. We were then consulted, NHP that is, by the contractor and the engineering consultant. We requested the contractor to test the power quality of the supply. He did this and found high harmonic content in the feed up to the 15th order. We advised that he either suppress the harmonic feed or feed the distribution board from a clean supply. So, to sum up in simple terms, higher frequencies cause lower capacitive reactance and potentially increase electron exchange between conductors of a different potential or the earthed trunking or conduits. Harmonic distortion can cause the fundamental frequency to act like a higher frequency for some of its influence on the electrical system. The longer the cable run, the greater the capacitive plate exposure for leakage to occur. The problem was solved by connecting to a supply source with little or no harmonic distortion. Some leakage would still exist, however, in highly diminished quantities so as not to affect the RCBOs protecting the circuit. So for those of you who do like to do your own investigations and calculations, the formula here, XC, or capacitive reactance in ohms, equals 1 over 2 pi frequency times C, C being the capacitance in farads. In short, capacitive reactance is inversely proportional to frequency. If we remove the imposed increase in frequency, we increase the capacitive reactance and reduce the capacitive leakage along the line. Finally, let's take a look at RCD testing. At times, there's confusion about how to test RCDs in many applications. Regular testing needs to take place both in domestic installations as well as commercial and industrial premises. AS/NZS 3000-2018 states that the first obligation is to test each RCD's operation by pressing the test button on the unit at least once a year, but in some situations preferably twice a year and sometimes more. Pressing the test button effectively causes a leakage between active and earth through an internal resistance and proves that the sensing system and the tripping mechanisms are fully operable. It's generally required that this function causes 2 times the rated leakage current value to flow for detection. There exists an exemption for testing of RCDs in new installations if there is no supply available at the time to sign off, which seems a little bit strange, and therefore this exemption is to be removed in the next amendment to the standard. AS/NZS 3760-2010, which is In-Service Safety Inspection and Testing of Electrical Equipment, specifies the testing procedures required when mandated by any body or authority. Most of the testing that's mandated is by way of workplace safety authorities in each of our regions. Section H3, Test Conditions, outlined the accepted methods and lookouts when testing RCDs. These included observation of the included rated voltage of the test equipment and compared to the rated voltage of the RCDs being tested, as the test results may differ if the voltage levels differ. Notes 1 through 6 a highly recommended reading for those involved in RCD testing. WHS and OHS regulations in each region basically say the same thing in the required testing procedures. Work Health and Safety Code of Practice 2015.165 states that, and I quote, a person with management or control of a workplace must take all reasonable steps to ensure that residual current devices are regularly tested by a competent person to ensure the devices are working effectively. A record of testing, other than daily testing, must be kept until the device is next tested or disposed of. End of quote. So individual regional bodies specify the record keeping generally documenting the person testing, the date of the test, and the test result. So so we look at tested at 1 times I delta n, the trip time, and pass or fail, and then the date of the next scheduled test. If the device fails a test, which is fails to trip or exhibits a time exceeding the 300 milliseconds in the case of type 2 devices, the RCD must be disconnected from the final subcircuit and retested. Now, if the device again fails a test, it should be removed and bench tested for verification. On many occasions, the tested breakers may fail the initial test because of the characteristics of the connected load, not because the breaker is faulty. Testers need to be very aware of these issues and their obligations to clients and suppliers. The table shown gives the mandated workplace health and safety regulations on RCD testing requirements, methods and options. These may vary in future state to state. Now, New Zealand at this point is not included in this authority table, but consult the local authority requirements if you are looking from New Zealand. This attached table is a typical report requirement outlining the identification of the workplace location, the RCD tested, the time, the date, the method, and the result, as well as the qualified person doing the test. Should there be an accident requiring investigation by the authority, it's essential that this type of record is up to date and factual. Incidents requiring investigation by and handling by the judicial system may insist on this documentation in the liability process as part of Workplace Health and Safety Act. So in conclusion, in this video we've looked at AS/NZS 2081 and the IT earthing system. We studied the approved earth leakage relays and why they comply to the specific requirements of the standard. We've covered the Holmgreen method of earth leakage detection for when things may get a bit difficult, and retrofitting 2-wire earth leakage relays without changing out the 4-wire toroids. We also looked at the cause of nuisance tripping in applications where long cable runs and harmonics are present, and a quick visit to the testing methods and obligations required by the relevant standards, both the wiring rules and 3760 with regards to workplace safety and OH&S regulations. We trust that the information delivered was of interest and will assist your business in the future. If you have any questions regarding this webinar, feel free to drop me a line at syoung@nhp.com.au or call our customer service consultants and ask for technical assistance on the subject. Now, don't forget to grab a look at the very informative webinar by Jamie Goddard specifically on devices called Enhanced Protection of Your People and Assets. Thank you. Thank you for taking your time, and thank you in viewing. See you next time.